Okay, and good morning. Let's start the class. Okay, so today we will talk about group. So we will introduce what is a structure called a group, and then to describe this, we will also talk about some other related structures. So, but before that, we need to talk about some introduction. Okay. So first of all, suppose that. So I want to define something called a binary operation. So suppose that A, B, they are sets. So if we have a function f that has this property that takes two inputs from the set of A, and then it is going to be mapped to an element in B, then in that case we say f is a binary operator. Is that okay? So in that case, f is a binary operator or operation. Okay. So for instance, if we take some elements f, let's say a1 from A, and then let's say take some elements a2 from A, then based on this function, we can compute the value of f of A, and then we will get something, let's say b1 from B. Is that okay? Now, but because this is a binary operation, so always it takes on two elements, okay, from A. We can also have an alternative way to write it. So we will put this f in the middle of the two items that we are going to operate, AF, A2. So perhaps this is something strange, but we are actually using this every day. So like the plus 1 plus 2 is equal to 3, actually the plus is a binary operator, right? So it takes two integer or two real numbers as the input and then computes the sum and then get a result. Is that okay? Or the multiply, it is also something like this. Okay? So sometimes, so if it is a binary operator, we usually, rather than using an English alphabet, an English character F to represent it, we will use some symbol to represent it. Like, we may think of this as some symbol like, so let's change it as a certain symbol. For instance, let's say we may use a star to denote this. So rather than writing star of A1, A2, we write A1 star A2. Is that okay? So we write A1 star A2 is equal to B1 instead. Okay? Good. So this is a binary operation. And then, okay. And then, so we have defined what is meant by a binary operation. Okay. And then we want to define something called closed. Okay. Okay. Now, if further, we have the set A is the same as the set of B, which means what? Which means the function star is actually mapping two numbers, okay, A1 and A2, to the same set A itself, then we will call this star a closed operation. Is that okay? So it goes back to itself. So after applying the operation, it goes back to the same group of items, then it is called closed. So it never gets away. So it is closed. Is that okay? Okay. Okay, and then if, so this is another thing. if the function star satisfies the following. For every A, B, C in A, we have A star B star C is equal to A star B star C. Is that okay? Then we call this an associative operation. If you are okay with this so far, could you please raise your hand? Okay, so associative view. So when it is an associative operation, we will use a shorthand notation. We just, because the order of applying this, whether we apply this star first or whether we apply this star first does not matter. So we will simply omit the parentheses because it will always give the same result, no matter which you want to apply first. So we will use this shorthand to represent this one. Okay? Okay, so let's see some example. Okay. So for instance, suppose that the hair color of a child is determined in this way. So we'll take a look of the mother and the father. Is that okay? So the color of the mother's hair could be light or could be dark. Is that okay? And then the color of the father's hair, let's say it could be light or it could be dark. And let's say the result is like this. So light, let's say we get light. Light, dark, let's say we get dark. Dark light, let's say we get dark. And dark, let's say we get dark. Is that okay? Okay. So we can talk about this hair color of a child. You can talk about this as a certain function like whatever. Okay, something like this. Okay. So we will have something like, so this table actually represents the result of light, dark. It is equal to dark, and then light is equal to light, and so on. Is that okay? Now, so first of all, if you look at this as an operator, so this is going to be a binary operator. It always takes two things as the input, and then mix them, right? And then this operator is also a closed operator, closed operation, because after doing the mixing, you are still getting a result either dark or light. Is that okay? So the set that we consider is dark or light. It has two elements, and after this, taking this operator on any two items in the set, we get one of the item in the set. So it is a closed operator. Is that okay? And is it associative? Now, associative is difficult. We really need to check. Okay, is it associative? So let's take a look. So how many cases are there? So we check whether light, whether this matter if I do this first or do this first. If I do this first, I will get light, and then light. If I do this first, I will have light, let's say cross light, so it is light. So this one is okay. So this is always equal to light, no matter which operator is applied first. And then let's say light, dark, light. What will happen? So if I apply this first, I will have dark. Dark cross light is dark. If I apply this first, this is going to be dark. Light cross dark, dark. Okay, so this is going to be dark no matter what happens. Okay, and then so we will check every case. In fact, if you look at this more carefully, when do we get a dark? When one part is a dark, we get a dark. Is that okay? So if I have something like A, B, C crossed together, it is actually asking whether there is a dark. If there is a dark inside, you get a dark. Okay, then in that case, no matter which part you apply first, you get a dark in the end. On the other hand, to get a light, everything has to be light. Is that okay? Then in that case, no matter which part you apply first, you get a light. So in that case, this operator is also an associative operator. Is that okay? Okay, good, good. Okay, let's see one more example. Okay, let's see another example. Okay, suppose that I have a new operator. Let's say, give it a. So let's say, okay. So let's say I'm going to define an operator of this one on a set of 4 items: alpha, beta, gamma, delta. Let's say alpha here, beta here, gamma here, delta here. So we have alpha, beta, and gamma, and delta. Is that okay? So let's say I have a delta here, alpha here, beta here, and gamma here. So let's say I have alpha here, beta, gamma, and delta. So let's say I have alpha, beta, gamma, delta. And let's say I have alpha, beta, and gamma, gamma. Is that okay? Okay? So I'm trying to define another binary operator. So this binary operator is like this. So this is a binary operator, and it is closed. Okay, reason. Okay, no matter what you apply, and you pick any 2 items, apply this operation, you get some item from the set alpha, beta, gamma, delta. So it is closed. Okay, but is it associative? Now, it is not associative. So this is just, I write it down randomly. So most probably it is not associative. Associative needs a very strong criteria, right? You don't care about the order of how you apply. So let's take a look of this result. Alpha, beta. Let's say we do this. And then the other one is alpha, beta. Okay? So if I do this, alpha, blah, 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 alpha, blah, 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 beta, then what do we have? So alpha, blah, 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 beta, I get alpha. Am I correct? So here, so this is going to be alpha, alpha. Alpha, alpha, I got delta. So this one, I got delta. And then how about this one? This one, I do alpha, alpha first. So I got delta. And then delta, beta. Delta, beta, I will got beta. Is that okay? Okay. So as long as there is one case which does not satisfy this associative property, then it is not associative. Okay? So associative is very, very strict. Okay, we need every triple of items. ABC could be the same. Okay, every possible cases of items, you still need to satisfy the equality over there. So it is a rather hard condition to follow. Okay. Good. Okay. So now, so in general, so here we are talking about binary operator, right? We can also have a ternary operator, quaternary operator. So because when we take more tuples, like A times A times A to B, then this is called a ternary operator. And then we can have n-ary operator as well. Okay. Now, in general, if we have a set, let's say a set A, and some operator, some closed operator, could be binary, could be ternary, whatever, but as long as it is closed, perhaps a plus, something like this, or a star, something like this. So it is a set. This is a set with some closed operator. Then we call this a algebraic system. Algebraic system. But for today's class, or for whatever we are going to study here, we are going to look at an algebraic system that has just one operator. So we will be looking at something like A with an operator star. Okay? Is that okay? So we are going to focus on this one. Okay? Now, there are many different types of algebraic systems. Some of them has very regular structure, very nice structure. And one of them we are going to define, it is called a group. Okay? So group is a kind of an algebraic system that has a lot of properties to be satisfied. And then, okay. But we are going to define simpler things first. The first one is we are going to define what is called a semi-group. And after we define what is semi-group, we will define what is called a monoid. And after we define what is a monoid, then we will look at the group. Okay. Okay. So what is a semi-group? Semi-group is when this operator is closed and associative. Associative. Is that okay? So in that sense, this is a semigroup. Does that make sense? Okay. And then there are other natural semigroups that we can talk about. So for instance, so I'm going to wipe this board around. Okay. Okay, so example of semigroup. So the first one that we have is the hair color case, the hair color example. Okay, another example. Let's look at something that we are more familiar. For instance, let's take a look of the natural number set. So natural numbers starts from 1, 2, 3 up to infinity, and then we have a plus. Okay. So if you look at this, then first of all, it is a closed operator. You add two positive numbers, then it is going to be a positive. You add two positive integers, then it is going to be a positive integer. It's closed. And then A plus B plus C, you can do whichever order you like. So it is associative. Okay? Okay, the third one, let's say, so we have all the strings, binary strings, let's say. So let's say we have the set of binary strings that we consider. And then we have this operator, concatenation. So you have a string, let's say 0, 1. You concatenate this with a string 1, 1, 0, 1. Then you get 0, 1, 1, 1, 0, 1. So it is like a concat. So you glue them up in order. Okay, so in that case, if you glue two binary strings together, then it is going to be a binary string, right? If you what? If you have three strings, A, B, C, you want to glue them together, you can glue A, B first, and then glue C. Or you can glue B, C first, and then glue A at the front. Is that okay? You get the same result. So this is associative. Is that okay? So even So for instance, or maybe you can have many examples. So let's say you have real numbers, let's say R, okay? And then let's say you have the operator max of two numbers, okay? So you start with two real numbers, the maximum must be one of them, so it is still in the real number set, so it is closed. So the max of ABC, no matter you do what, you compare AB first, you also can compare BC first, you get the same result. Is that okay? So max is also an example, okay? So this is the so-called semi-group, okay? Now next, from semi-group, we can make it more complicated. So if semi-group, if a system is a semi-group, but it has one more constraint, one more property, then it will be promoted to the next class called monoid. So a semi-group with something called an identity will become a monoid. So what is an identity? So definition, okay. 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 Okay, so definition. So an element E in the set A is a left identity if for every element A in A we have E star A, sorry, is equal to A. So here we assume we are looking at the system A star. So we are considering this algebraic system A star. Is that okay? Now, if an element E taken from this set A has the property that when we multiply, you can think of this as like a multiply operation. When we multiply it on the left-hand side of any element A, it gets back to A. Then it is called a left identity. Okay? So we can also talk about a right identity. F in A is a right identity if for every A in A we have A star F is equal to A. Is that okay? So this is called a right identity. Is that okay? Okay, but it is not an identity yet. We have left identity, right identity.